All right, guys, it's Monday, or not, it feels like a Monday. It's not Monday. It's Tuesday morning, February 9th. We are here in Math 8, and we are going to continue where we left off after our long weekend, our nice little break. We are on lesson 3-4. So if you're following along in your workbook, which I would recommend, it's going to be 3-4 is the lesson. It's going to be towards the back of the workbook. I don't have one with me. Unfortunately, I left my notes at school and left my copy of the textbook at school. They didn't really look ahead to see the weather forecast, and obviously we have like 3 or 4 inches of snow out there. So I'm home today, just like you guys. And I don't have my notes, but that's okay. We figured out that we left off with 3-4, so we're going to keep rolling here. Um, and I'm going to project my Savas program. But again, I do recommend that you guys follow along in the textbook, and also want to remind everybody that you do have assignments in Savas. A lot of you guys that are on the call right now are caught up, but there was a new one that posted on Thursday. Okay, it was after we talked about what is a function, right? So last week we talked about functions, and for every input there's only one output. That's the definition of a function. Um, so there was an assignment that gave you some data points, some series of data, and asks you to determine whether or not they were a function. That's in Savas. Um, so make sure you guys go in and do that. And again, those of you on the call right now, you guys, I think, are fairly caught up, but I haven't checked to see who did this most recent assignment yet. It just posted on Thursday, so you might have one assignment that's still due. Anyways, let's take a look at what we got here. We are looking at creating linear functions from data. Okay, so we're going to take a look at today's challenge here, just to get us thinking a little bit, and then we'll go into some problems. But you have a chart here with a bunch of um, different banquet halls, or maybe it's one facility, and they have lots of different banquet halls. Like a lot of times, a place that hosts events will have like a couple of big rooms, a couple of small rooms, and a couple of medium-sized rooms, right? So obviously, it looks like the Bronze Hall. Um, they all have different prices, and they all have different capacities. The Bronze Hall is the smallest, right? Capacity is 200. The Diamond Hall is 375. Um, and they all have different capacities and different costs per plate, right? So that's the cost per dinner. Like if you have an event, you typically, sometimes you don't. I mean, if you're having a conference or whatever, you can just rent the space. But if you're having like a wedding, you're also going to have them serve dinner. So there's a cost per plate to invite your guests. Um, so which banquet hall do you think is the best to hold a fundraising dinner? What factors may influence your answer? Um, what it's asking us to do is kind of look at these and start to think about developing functions for the cost of each one of these um, banquet halls, right? So you notice that the biggest hall, the Diamond, has no cost. It's free to rent. It holds 375 people, but they charge you $170 per person to serve dinner and beverages and whatever, right? That's a really expensive. Like, yeah, there's no fee, but it's $170 per person to uh to serve dinner. And obviously, like that's a requirement. If you're going to rent out the Diamond Hall, I guess you have to serve dinner. So they're going to make their money off of the food. So if we're going to write a equation for this Diamond Banquet Hall, we could start out by, let's say D, the price of Diamond equals, there's no rental fee, so 0 plus it costs $170 per person, and they hold $375. So if we want to find the total amount, let's say they sell it out. Let's say they invite 375 people. They fill the whole banquet hall, and they're going to charge $170 per person for food. What are we going to do with these two numbers right here to find the cost? What do we do with these? Do we add, subtract, multiply, or divide them?
To add. Do we add?
We don't add because then that would get really repetitive, right? We are adding, like, we would have to add 170 375 times, right? There's 375 people, and each one of them gets charged for $170 for their meal and drinks. So does that kind of tip you off? Does that give you a hint? Instead of adding, we're going to do something that makes it really easy to add large numbers. I kind of gave it away. You would have to add 170. Yeah, you'd have to add 170 375 times, right? Because each person gets charged 170. So 170 plus 170 plus 170 plus 170. You have to do that 375 times. That's obviously times is the same as multiply, right? So I'm going to write this. That right there is a function of how much money it's going to cost us to rent the Diamond Banquet Hall. Okay, so obviously there's no rental cost, so that was the zero, and then this 375 times 170 ends up being our total cost. You guys are not going to be able to see the calculator, but I'm going to punch this in the calculator real quick. 170 times 375 is $63,000. That's expensive. 63,750. That's a lot of money to rent that, right? It's free to rent the hall, but man, they get you on food. They charge you $170 a plate, which seems to me like it's pretty outrageous price. So it's always brings up a good lesson. It's always good to calculate this stuff before you go committing to buy something, because something might seem like a good deal because they'll say, oh, it's free to rent. Or like, cell phone companies, they'll say, oh, you get a free phone if you sign up, if you switch to whatever, AT&T or T-Mobile or whatever, we'll give you a free phone. Well, they're probably going to end up charging you a lot more over the long run. There's going to be some clause or some thing in the contract where you get charged a lot more for the service, because the saying goes, there's no such thing as a free lunch, right? If you get something for free, you're going to end up paying for it in another way. Let's look at how much would it cost to rent the silver banquet hall. I'm going to write an equation for the silver banquet hall down here, and we'll see which one is less expensive to rent. So the silver equals, well, the rental fee is $1,500, so we're starting out at $1,500, right? That's our starting point. That would be our y-intercept if we were writing a linear equation. And then we have to add the amount of food cost, right? 250 people times $75 a plate. As somebody who's been married, that seems about maybe a little high, but like I think the place we had our wedding, they charged $50 a plate to serve food and beverages for everybody, and that obviously pays for the food, and then it pays for all the workers, that are serving the food and serving the drinks and all that, right? You pay $50 a person in addition to renting out the banquet hall, right? So that's like this is a pretty reasonable real life example right here. So let's figure out what we got here. I'm going to do 250 times 75 in my calculator. 250 times 75 is $18,750. And then we have to add the rental fee plus, 18,750 plus $1,500. $20,250. Okay, so it is far less expensive to rent the silver room than it is to rent the diamond room. Okay, so the only thing that would influence our decision here is how much do we think these people are going to donate, right? Because it's a fundraising dinner. So what you're doing is you're renting out the space, and maybe it's like, I don't know, maybe it's a fundraiser for raising money for the school, like for the athletic department to have, to fund the sports teams. Or maybe it's a fundraising dinner for like a charity that raises money for cancer research or whatever. So if you think that these people that are getting invited, I don't know, maybe they've got lots of money to donate. Um, if you think they've got lots of money to donate, you obviously want more people there, right? You want to invite as many people as possible. If you think maybe these people might only donate, a few $100s a person, then you'd obviously want to go with the one with the less cost, with the least amount of cost, right? But it all depends on how many people you think are going to come and how many people and how much money you think they're going to donate. If you're inviting Bill Gates and Warren Buffett and Kanye West and I don't know, who's the guy who owns Tesla? What's his name? Elon Musk. If you got all those people coming to your fundraiser, maybe Diamond's the way to go because you'll gladly spend $63,000 because all those guys are millionaires and billionaires, so they'll probably donate. Maybe they'll donate $1 million or something. So 63,000 is a relatively small cost. If you've got regular old average people coming to this thing that may only donate a few $100, you want to go with the smaller cost, right? And this is a little bit like these as it goes higher. This is not necessarily a real life example, but these two right here are pretty standard for like renting a hall. Like I said, I think I paid $50 to rent my $50 a plate. I don't know what they charge us as the rental cost, but it was something like this. So when getting married is expensive, let me tell you that. It wasn't quite this much, but it was a lot. Anyways, I digress. So we're starting to think about making an equation. Does it make sense how I got this information? Do you guys have any questions about how I got this information? Right? The cost to rent the Diamond Hall came from this information that they gave us right here, right? No rental fee plus $170 times the amount of people it holds or the amount of people we invite, right? And then this one for the Silver Hall was the $1,500 rental fee plus it's 250 people capacity, and we multiply that by $75 a plate. So we are going to go into the lesson and we're going to start looking at how we do this. We're going to start looking at how we create a function from information in a different format. Could be a graph, could be a chart, could be a word problem, right? But we want to know how can we make a function and represent that information in a mathematical expression, okay? So we got our 2-minute video here to introduce the lesson. I'm going to go ahead and hit play.
How can you use a function to represent a linear relationship? Think about this question during the lesson. A plan for a skateboard ramp shows that the plywood for the triangular sides of the ramp should be cut such that every 9-inch increase in height is accompanied by a 33-inch increase to the base. What is the height of the skateboard ramp? The first step is to use the graph of a line to represent the situation and to determine the slope of the line. Show the height on the y-axis and the length of the base on the x-axis.
All right. So again, this is we're moving into real life applications of this linear function thing that we learned, right? We spent the last week or two learning about y equals mx plus b, right? That was 2 weeks ago. The linear equation, right? Y equals mx plus b. Mx, the m would be your slope, right? And the plus b would be your starting point, your y-intercept. So in this question, they've literally given us the slope, the rise over run. The increase in height is 9 inches, and the increase in the length of the base is 33 inches. So it's literally telling us this ramp goes up 9 and over 33, right? It's positive because they don't have any negative signs in there. So it's up 9 because it's positive, and then right 33. So on our graph, they're literally going to graph. They go up 9 and over 33. And you notice in the bottom here, anybody notice what this is counting by? Each square? This is tricky, but do you see a pattern? What's it counting by? Each square. It's not counting by ones, obviously. One.
It's counting by 22. I don't feel like it.
Yeah. No, you're right. It's counting by 22s.
44, 66.
You're absolutely right. 22, 44, 66, 88. So these individual squares are counting by 11s, right? Because 11 is half of 22. So yeah, you're right. But if we count by 11s, we go 11, 22, 33, 44, 55, 66, 77, 88. Or just what they have labeled is counting by 22s. But look why they did that. Because the height is 9 inches, the rise is 9, and the run is 33. So if we count by 11s, 11, 22, 33, this line is exactly 33. So you're going to go up 9 and over 33, and our first point would be right there, right? So that's why they set the graph up to count by 22s or 11s, depending on how you look at it. But yes, good. It was by 22s. Absolutely.
We know that
All
when
right.
the height increases by 9 inches, the base length increases by 33 inches. So the point with coordinates 33, 9 represents one possible base length and height of the ramp. A second increase of 9.
All right. So again, this is the slope, right? Just like we were saying, the rise over run. And this is all review kind of from last week, that what we did with linear equations. We're just now taking it and applying it to a real life problem, right? Of a ramp that the height of the ramp is 9 inches and the length of it's 33. It went up 9 and over 33. We're still doing rise over run. And then we're just graphing that as up 9 over 33.
9 inches in height and 33 inches in base length represents another possible height and base. The line shows that for every 9-inch increase of height, the base length increases by 33 inches.
All right. Are our memories being refreshed a little bit from doing this? Because we did some homework over this, right? Where you guys were given a linear equation and you had to graph it, or you guys were just given the base, or not the base, the y-intercept and the slope, and you just had to graph it, right? In this particular case, our equation for this line, our y-intercept is 0, right? Because this first starting point is right at the origin. It's at 0, 0. It's right in the middle. So we don't even have a y-intercept. If we were to write this as y equals mx plus b, our plus b would just be plus 0. It just wouldn't even be there. But our slope would be 9 over 33x. Like if we wanted to write an equation, I'm going to switch over here to the Jamboard real quick. If I wanted to write the equation for that line, in y equals mx plus b, right? And we know the m is the slope because the slope is always with the x. And we know the b is the y-intercept, or the starting point, right? So I'm going to write y equals, we know our plus b was 0 because, well, let's just do that last. We look back at our slope was up 9 over 33. right? So our slope is 9 over 33, rise over run. You got to put the x with the slope, right? Because the x always goes with the slope. That's why I did that. And then our plus b would just be plus 0. So we went up 9 over 33. And you can see down here, our plus b is 0. So if I go back to the whiteboard, I have my slope right here. My m is up 9 over 33. We have to put the x with it because the x always goes along with the slope. And then our plus b is simply 0 because as we see on the graph, our origin is at the 0, 0, right? So that is the equation. We don't even need the plus 0, okay? We don't even need this because plus 0 is nothing. So our linear equation would just literally be that. Now you can reduce that because both of these are divisible by 3, right? 9 divided by 3 is 3, and 33 divided by 3 is 11. So our reduced simplified equation would actually be this, right? But these are the same, these are equivalent expressions. 9 over 33 and 3 over 11 are equivalent fractions, right? If you punch this into delta math, it would tell you your answer is technically correct, but you need to reduce or simplify, right? Because you could, both of these numbers can be divided by 3, they can be factored. There's a common factor there. And you learned all about how to reduce fractions earlier on in your careers in math, probably when you were in 5th or 6th grade. But is that kind of making sense? How we wrote this equation right here, y equals up 9 over 33. Let me go back to the graph. We started at our y-intercept was 0. So if we were going to write this equation, we see that it doesn't even have a y-intercept. It doesn't have a plus b. So we know that that means it's at 0, right? We know that that means it's just right in the middle. And then we went up 9 over 33, up 9 over 33, up 9 over 33. We plotted the points, and we can see that it makes a straight line, which we also know that if we have a straight diagonal line that passes through the origin, we have a proportional relationship, right? We talked about that like before Christmas break. So this is all coming together. This is all stuff we've been talking about kind of all year, and we're putting it all together right here, where we have a slope, a y-intercept, a proportional relationship, the origin, all this stuff is tying in to make equations. All right, let's go to the next section.
So the slope of the line is the change in height, which is 9 inches, divided by the change in base length, or 33 inches. The slope is 9 divided by 33, which simplifies to 3/11. Now, let's use the slope to write an equation for the function shown in the graph.
Oh, we already did this, so we don't even need to do this, okay? We literally just did this right here. We figured out that our slope was 933. We put it with the x, right? We don't have a plus b because our plus b is at the origin. It's at 0, 0. So our final equation for this line is right here. Y equals 3 over 11x. There's no plus b. There's no plus anything because it's plus 0. So why write it? Plus 0 is, it's nothing. Plus or we don't even need to write plus or minus 0 on the end of it. All right, so since we've already done that, let's just keep going.
The equation is y equals 3/11 times x. Y represents the height. X represents the base length. And 3/11 is the slope. Now, use the equation to find the height for a base length of 110 inches. Which variable should be set equal to 110?
Select your answer.
All right, so it's asking us, we need to find what the height is if the base is 110. So which one of these variables is y or x, the base length? right? It tells us the base length is 110. Is y the base length or is x the base length? Look at the graph and find out right here, like these two axes right here, they're these axes, right? One of them is the y-axis, one of them is the x-axis. Which is the height and which is the base length? Let's look at that, because it says the base length is 110. So is y the base length or is x the base length? What do you guys think?
The
We
X.
have labels here on the graph too. Yeah, you're right. You're correct. X is the base length. So thank you, Brandon. Right? We can see that they even label this right here. Sometimes they won't label it because as you get up into 9th, 10th grade, they might start to expect you to know that the y-axis goes up and down, right? And I always say the way my teacher used to tell me to remember it back when I was in 7th grade, 8th grade, whatever, is y to the sky, right? The y-axis is the one that goes up and down, y to the sky. X goes left and right, or along the ground, or horizontal, right? This is horizontal and this is vertical. Vertical to the sky, up. That's the y-axis, right? So the y-axis is height, and they label it as height. The x-axis right here, it says base length. So you're right, Brandon. It's x. So since we know that x is the base length, all we need to do here, I'm going to check x. And then I'm going to pause it because I want to do this. They're going to show it, but I want to do this. All we need to do is we need to put 110 into this x slot, right? You can think of this. Let me clear this Jamboard here. And we have our equation, right? Y equals 3 over 11x. We can think of these as blanks. Blank equals 3 over 11 blank times blank, right? We can think of these as blanks. If we punch in, if they told us x equals 110, right? They said the length of the base equals 110. All I need to do is put 110 into this x slot. Do you see how that works? I plugged in 110 for x because they told me that the base length was 110. Now all I need to do is do this math. Okay. I just punch in for I can really do this in my head. If I could punch this into a calculator, I could do whatever, but I see something right away here that's going to make this problem really easy for me. Does anybody notice? Let me rewrite this. We have blank equals 3 over 11 times 110. I'm going to write it a little bit in a different format. Not a different format, but I'll write it so that it's easier to look at. Does anyone notice anything between these two numbers? You've got, so what this is, you can look at this as 110 is the same as 110 over 1, right? So that makes it a little easier for us to look at. We have two fractions now. A whole number 110 is the same as 110 over 1. So look at this. How many times does 11 go into 110? That's not a division fact we know off the top of our head, right? We only learned our times tables up to 12 times 12. But, well, I shouldn't say that because technically it is a division fact we should know. What's 110 divided by 11? This is actually really easy because if we look at these, we see an 11 here and an 11 here. So what this really ends up being is this goes into 110 10 times, right? In effect, these 11s almost cancel and that becomes a 1. Well, we still have a 0 here, right? But anytime you see like 110 divided by 11, or if you had 240 divided by 12, right? Well, you know that 12 goes into 24 twice. Keep your zero. That answers 20, right? So that actually was a pretty easy problem. They set it up for us so we could do it in our head. So we have ones on the bottom now. 1 times 1 is 1. 3 times 10 is 30. So our answer should come out to be 30 here. When the ramp is 110 inches long, the height is going to be 30 inches, right? Does that make sense? All I did was plug in the information they gave us for the length of the ramp. They said the ramp should be 110 inches long. So I just put in 110 in the blank for X, and then I solved. 311, if you punch that in a calculator, 3 over 11 times 110 equals, it would say 30, right? Or we did it in our head, because it was kind of an easier problem. It was a clean, even number with clean, even numbers that were divisible by each other that we know.
Substitute 110 for the variable that represents the base length, which is x. Then simplify to find that y equals 30. Our results show that the height of the skateboard ramp is 30 inches when its base length is 110 inches.
All right. So that's the end of the video. Does everybody see how that works? This is a good, like, they didn't show all the math of how they got it, but they show how they just substituted 110 into the X value, or the blank, so to speak. They filled in the blank where X is because it told us the length is 110, so they just put in 110 for X because we knew that X was the length and Y was the height back from the original graph, right? They labeled the Y-axis as height and the X-axis as length. So we know that X length, we just put in 110 and we solve it, okay? And so that's why we do these equations, is once we have the equation, we can figure out how high this is going to be for any length. If I said, I'm going to make a 500-inch ramp, like a huge, gigantic ramp for like the X Games or like some skateboard competition, right? They're going to make one of those huge ramps. Like there's a competition in the X Games where they go down that giant ramp that's like 70 feet high or whatever, 50 feet high. And then they like do tricks off, like, it goes down a hill and then it goes up a huge hill and they do tricks off it and they try to do like 720s and 900s and flips and stuff. Like they're going to build a 500-inch ramp. Like I could easily figure that out because all I have to do is 3/11 times 500, which comes out to be 136.36, right? 136 inches high. Okay. Some of these ramps, and I mean, you guys know what I'm talking about. Maybe if you've ever seen the X Games on TV in the summertime, like, this like giant, huge, here we go. Here's a good picture of it. I want to open image in new tab. Right, here you go. They've got this giant ramp where you start way up at the top and then you go down and you ramp off of it. You jump over this, you get another little gain of speed going down this ramp, and then you go up this huge ramp and try to do like a 720 double flip and then land, right? It's kind of cool to watch. I'm not really big into like skateboarding or anything like that, but when it's on TV, I always find myself watching because it's pretty crazy. So like, maybe we're talking about they're building this ramp right here for them to launch off their initial jump. That's, maybe it's 500 inches. We just said it's 500 inches long and 136 inches tall. Is this ramp right here. And then this ramp is obviously like huge. This ramp is like 10 feet high. So they get like tons of air time off of it, and they do all kinds of spins and flips and whatever. Let's go back to the, did I lose my presentation? I think I did. Let me present my screen again. I lost my presentation here. That's okay. All right, we're back. We're back online. Let's go to the next one. You know what? There's a try it. Yep, here's what I want to do. All right, so it's asking us to graph. It gives us this information right here. Skateboard ramp has a base length of 110 and a height of 30. Slightly different. Oh, this is the same info. Is it the same info they gave us? I don't remember. It's very close. They're just asking us to graph this. They're asking us to graph the information they just said. The skateboard ramp has a length of 110 and a height of 30. So they're telling us our slope of this line, right? Up 30 and over 110. So I'm going to put my initial point. Well, here's what we can do. We can put our initial point at 110 comma 30. Okay, I'm going to put a point. Well, there's already a point right here. What on earth? This height is all wacky. It's height in inches. It's 110 and 30. Like, this graph doesn't even go that far. Maybe we need to zoom out a little bit. Okay, here we go. Maybe this will work. Okay, so we can put a point here at right here. This looks like about 110, 30, right? There's a point. All right, 30 inches high and 110 inches long. Our point, our coordinates would be 110 comma 30, right? 110 comma 30. So then it says a plan for a new ramp requires that for every 3 inches of height, there are 15 inches of length. So graph the function. So it's telling us again our slope, 3 inches over 15, 3 comma 15. All right. Oh, so let's just do the new ramp. Maybe that's, they gave us this information to throw us off and it works. Okay. It wants us to graph the new ramp. They're going to build a different ramp. And the rise over run, the slope is 3 up and 15 over, right? The height is every 3 inches of height, there are 15 inches of base length. So we go up 3 and over 15. So let's just go back to our original graph here. Okay, so we're obviously going to start out at 0, right? So we're starting out at 0. Now we're going to go up 3 and over 15, right? And notice that these are counting by tens, right? 10, 20, 30, 40, 50. So 15 would be halfway between 10 and 20. So this right here is a graph of the new ramp, right? We start at 0. We have no intercept because we start right at 0. Try to put that right on the line. There we go. And then it told us the slope. Rise is 3, run is 15. For every 3 inches of height up that the ramp goes, we go over 15. We have a 15-inch length. Okay, up 3 over 15, up 3 over 15, up 3 over 15, and so on. So then it wants us to write its equation. Okay, so we graphed this line with this information right here. 3 inches of height per 15 inches of base. Now we need to write an equation. So I'm going to start by putting our linear equation form here. Y equals mx plus b. So now we need to find out, what is this? What is our M? What is our slope, right? Our M is our slope. So what was our slope? Can anybody give me the value for the slope? Again, they told you the information you need right here. For every 3 inches of height, there are 15 inches of base length. Here's the height and here's the base length. What was our rise over run here? What was our rise over run to get from this point to this point? We went up 3 and over 15, right? So that's our slope. Up 3 over 15. And since it's up, it's positive, right? If we went down, it would have been negative 3 over 15, but we didn't go down. So our M is our slope. So it's going to be 3 over 15. Hey, that's cool. It even makes a fraction for me. X plus, what's our B? Where was our starting point in this graph? What is our y-intercept here? Where's our starting point? Where did this line cross the y-axis? That is our plus B, our y-intercept. What is the y-intercept here? You guys know this. We learned this 2 weeks ago. What is our y-intercept here? We know that our slope is up 3 over 15, up 3 over 15, up 3 over 15. What's our y-intercept? It's right here. What is that? If it was down here, it would be different. If it was down here, what would it be? You guys know this. Think about this. We spent a week and a half on this stuff. What is our y-intercept of this line right here? Isn't it 0? This point is right at 0 on the y-axis, right? It is at the origin. It does not have any height. It didn't go up any, it didn't go down any. It is right at 0, right? And that makes sense because the beginning of the ramp starts at the ground. You wouldn't have a very good ramp if the ramp started at positive 3. There would be a like 3-inch like bump at the beginning of the ramp, right? You have to have your ramp start at 0, and the point is right at 0. That is the y-intercept. So if we're going to put that in here, we would put plus 0, but we don't need to put plus 0. This is unnecessary, right? If it were like this, then we would need to put plus 3, right? Because we definitely need to tell everybody this starting point, this intercept is positive 3, but it's not. It's right here at 0. So plus 0 is obvious. If I have a plus 0, I don't even need to write it, right? I can just get rid of it. Now, technically, you could reduce this as well. 3 over 15. 3 and 15 are both divisible by 3, right? 3 divided by 3 is 1. And 15 divided by 3 is 5. So when we reduce this, our linear equation is going to be y equals 1/5 x. 3/15 x is technically correct, but we need to reduce it, okay? Our reduced final equation for this line is y equals 1/5 x. It doesn't have an intercept. So we know that that means that it is plus 0, right? So we know that it means it starts right here. It starts at the origin. If it doesn't have an intercept, it starts at the origin. And then we go 1 over 5. So if we were to go 1 over 5, right? Because this is tens, so this is 5, 10, 15, 20. Up 1 over 5, up 2 over 10, up 3 over 15, up 4 over 20. And it seems like our line is holding true, right? So this right here would be a correct answer for the equation of this line. Y equals 1 over 5x. Does everybody understand how I got that? Is everybody with me? All right, let's go on to this next try it. Okay, this one's an easy one. Explain why the initial value and the y-intercept are equivalent. Well, we've kind of been explaining this for a couple weeks now, ever since we started doing linear equations. We know that the y-intercept is our starting point, right? Our starting point where we're going to start graphing the line. If we have a equation, right? If we have y equals 2/3 x plus 3, we know that the one with the x is the slope because it has x with it, and we know that the one with the without the x is the y-intercept, and we also call that the starting point, right? If we're going to graph this line, the first thing we're going to do is to go to +3 and put a point, right? If we're graphing this on a graph, the first thing we would do is put a point right here at +3. That's our starting point. So our starting point, initial value, starting point, right? Initial and starting are the same thing, right? Not the initials of your name, the initial, like the first. The word initial means the first, right? That's why we call it initials, because it's the first letter of each part of your name, right? Like my initials are BL, Ben Levine. BL, the initial letter in my name is B and L. So my initials are BL, right? The starting point and the initial value are the same, the y-intercept, right? All three of these things are the same when we're looking at equations. The y-intercept, the initial value, the starting point, all that stuff is the same. Just like when we were talking about slope, you know that slope is the same as the unit rate, which is also the same as the proportional constant. If you hear any of those, which is the same as rise over run. All of those things are the same. Slope, unit rate, proportional constant, and rise over run are all the same thing. Just like initial value, y-intercept, and starting point are all the same thing. There are three different ways of saying the same information. So that's complicated. It's a lot to process, but we need to, we just have to know it. We just have to know it. And that's why we're going over this again. I know we went over this 2 weeks ago when we did linear equations, but that's why we're kind of reviewing this to tie it into the new stuff, right? We need to know that slope and unit rate and constant and rise over run are all the same. We need to know that initial value, starting point, and y-intercept are all the same thing. Because when they give you these word problems or these problems with like a data table or a chart or a graph, we need to decipher the information they're giving us and be able to figure out how we write a linear equation or how we write a function. I'm going to leave this up for just a second or two more so you guys can all, this yellow, right? 3 yellows are all the same, and the 4 purples are all the same. All right, let's go to example 2. Write a function from 2 values and try it. All right, the cost to manufacture 5 toys is $17.50. The cost to manufacture 10 toys is $30. Construct a linear equation in the function, linear function in the form of y equals mx plus b that represents the relationship between the number of toys produced and the cost of producing them. The first thing we need to do is determine the slope or the rate of change, right? Determine the constant rate of change. So what they did was they did the delta x and delta y, right? The change in x and the change in y. They put the change in y on top, and we did this 2 weeks ago. Oh, right? It's y2 minus y1. Sorry about my handwriting. Over x2 minus x1. Right? That's what they're doing here, right? This is the change in y. How high or low did y go? What was the rise? And this is the run. What was the change in x? What was the change left and right on the graph? That's what they did here. So, right, y2 minus y1. The change in the cost was 30 minus 1750. Right? 30 minus 1750 is 1250. The change in the number of toys they made was 10 minus 5. Right? 10 toys and 5 toys. So the constant rate is 12.5 over 5. They reduced that to 2.5 over 1. If you punch in 12.5 divided by 5 and you're obviously going to get 2.5. 12.5 is really 12.50 is what we're talking about, right? $12.50 divided by 5 toys. So it's $2.50 a toy. It costs this company $2.50 per toy to make the toy on their machine. Okay, it's like a toy car or whatever they're making. Radio control car. And then we can set this up backwards to solve for B and find out what our y-intercept is, okay? So look what they did here. We know that this information is true because it told us 10 toys cost 30 bucks. So we subbed in 10 toys into the X and we subbed in 30 bucks into the Y. And now our only information we don't know is B. So here's what they did. Here's how they figured this out. Let me go to the Jamboard. They subbed in, they had y equals 2.5x plus b, and we don't know what b is though. We have too many variables that are unknown. So what we did was we know that in one set of data, y is 30 and x is 10. So we just plug that in. 2.5 times 10 is 25, right? Because we're just moving a decimal. Anytime you multiply by a power of 10, you're just moving the decimal, right? So this really just moves over one space. But I showed you on the calculator, 2.5 times 10 is 25, right? If you get confused about moving decimals and stuff like that, you can always just check your work and make sure you're right. Okay, so now we have 30 equals 25 plus b. Now we're solving for what's our b, right? 30 does not equal 25, obviously, so we need to put something in here to balance it out. Well, it's pretty obvious that this is 5, right? 25 plus 5 is 30. If we wanted to do that mathematically, we'd have to subtract 25, right? Whatever we do to one side, we have to do to the other side. 30 minus 25 is 5. So it works out that b equals 5, right? That's how they did that. I wanted to show you guys how they did that because they don't really show the work in detail, okay? So we figured out based on the slope we found and the data they gave us for one of the data points that the y-intercept is 5. So the final function is y equals 2.5x plus 5. 2.5x was the slope that we found from the change in y divided by the change in x. And then we solved for b. We solved for it. We got it as 5. So what does this mean? If we have a function right here that says y equals 2.5x plus 5. This is really 250, right? It's 250 a toy to make the toys. Well, what do we call this? What's another word for this y-intercept? If we were going to graph it, what is this? Is this our slope or is that our starting point?
Is that our slope?
Our slope's always attached to x, remember? So this is the starting point. Yeah, the slope is always the one attached to x. So that's the slope. This is the starting point. Well, both of these things are in dollars, right? It costs $2.50 a toy, and this is $5. So what this really represents is the starting point, which is the cost of the cost to turn on the machine, right? It costs $5 just for them to turn on the machine. And sometimes, you know, the machine has to be booted up. The machine has to kind of initiate a startup sequence that maybe uses a lot of electricity, or maybe you have to refill it with the plastic resin that they're going to use. Like, right, it costs $5 to fill it up with plastic resin so that it can start molding these toys. All right, whatever this represents, it represents that it costs $5 just to start the process. Maybe $5 is the amount of is the cost of the plastic they're using to build the toys, right? So as soon as they fire up the machine, it costs $5 to fill it up with plastic resin, and then it costs $2.50 per toy. So maybe this is the cost of the electricity to run the machine, right? They have to plug it in, and it's using electricity, about $2.50 worth of electricity per toy. So their final cost is the cost of the plastic plus the cost of the electricity. So if they make one toy, if I plug in 1 into X, $5 plus $2.50 times 1 is $2.50. The cost of one toy is $7.50. Now, if they keep going, their cost is gonna drop, right, per toy, because if they do 10, then it's 25 plus 5, so Y would be 30. The cost to make 10 toys would be $30, and that was one of the data points they gave us, right? So I know these are tough sometimes when they give us like the real life situations and the word problems and the data and stuff. You guys really, you aced the ones where they just gave you the information, right? You guys are doing great graphing these linear equations. Like if I gave you on Delta Math, if I gave you y equals 4 over 7x minus 3, you guys knew right away by the end of the week, okay, what do I do? Minus 3 is my starting point. So if I'm on my graph, I'm going to go down 1, 2, 3, 3 spaces down, and I'm going to put my point, and then my rise is 4 and my run is 7. So then I'm going to go up 1, 2, 3, 4, and then I'm going to go over 7, 1, 2, 3, 4, 5, 6, 7, and I'm going to put my second point right here, and I'm going to connect the dots. You guys all know how to do that. You guys aced this. The next step is we have to be able to put together this information from word problems or data they give us, or a chart or a graph or something like that. All right, that's what it's working on. That's what we're trying to develop this week as we go through here. So let me see if I can do one more here. I think there's only one more example here anyways. Oh, there's two more. We'll do one of them. All right, let's do the one from the graph, and then we'll wrap it up here because we got only about a few minutes left. The graph below shows the relationship of the height of a burning candle over time. What function models the relationship? You guys have all seen a candlestick at the beginning. They start out really high. If it's one of those like long, skinny candles, like the old school kind of candles, like that people light at Christmas, they start out. They might be a foot tall. They might be 12 inches. This one starts out at 10, right? The starting point is 10. Okay, well, there's a clue right there. The starting point is 10, the initial height. So the initial height is one of the pieces of data we need to write an equation for this, okay? And then you can see it drops over time because the candle burns. The flame burns up the wax, and eventually the candle starts getting smaller and smaller until it finally runs out of wax at 0 and burns out. So if our starting point right here is 10, the initial height, what's that going to be in our equation? Y equals mx plus b. What's our starting point here? Is it m or is it b? Y in linear equation form, this is called slope-intercept form or linear equation. Is m the slope or is b the slope? And is m the intercept or is b the intercept? Which is which? We're looking for our y-intercept in this particular, right? It said the initial value is 10 inches high. Does that go with the m or the b? I know you guys know this. You might just not be paying attention. Which one is our starting point here in this equation? Is it m or is it b?
B.
Right. B is the starting point. So when we start to write this equation, y equals, we know that our initial height right here, our initial value is 10. So our y-intercept is 10. And if we look at this line, look, the y-intercept is 10, right? It is crossing this y line at 10. So we know when we start to write this equation that the end of this is going to be plus 10, right? Because this right here means that this line will cross at plus 10, which it does, okay? The next thing we got to figure out is what's the slope. The slope is what's attached to x. So I'm going to go ahead and put the x in there. And then we have a blank here that we don't know yet. We don't know the slope, right? We don't know the slope. We don't know what it is. So let's go back to the line. We got to find out what the slope is, okay? So this is counting by ones, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is counting by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's figure out our slope. This one's going to be real easy because this very next point right here appears to be right on a grid line, correct? Am I right or am I wrong on that? It looks like that point right there is on a grid line. At 1 hour, right, over 1, at 1 hour, our height is 9. So to get to this point, what was our slope? How many up or down and how many over? What was our rise and what was our run? To get from 10 to 9, what was our rise, first of all? What was our rise? How many spaces up or down did we go?
1.
1, right? Yeah, except did we go up or down?
Up.
We started here at 10 and we ended up here.
Oh, down.
Yeah, so we went down 1, right? We went down 1 and then we went right 1. Does everybody agree with me on that? We with me? We went down 1 and right 1. So what's our slope going to be? Rise over run is how far up and down over how far right. So we went, if I go back here, my rise was -1 because we went down 1, right? It's -1. And my run was 1 space. I need to simplify this. The last thing I need to do is simplify this. Negative anything divided by 1 is itself. So I can clean this up and just say y equals -1x plus 10. I could even clean it up more and just say y equals, and clean it up more and say y equals -x plus 10, okay? But I'm going to leave the 1 in there for now, okay? Do we see how we got that? We went down 1. Now I'm still erasing. Sorry. We went down 1. So we have -1. And then we went right 1. So we have a 1 here. Obviously, 1 divided by 1 is 1. And we still have our negative sign. And then we still have our starting point of plus 10. So if we were to graph this line right here, we know our starting point is plus 10. So we would put our first point right here at plus 10 on the y-intercept. And then we go back and say, okay, our slope is -1. Whenever we see a whole number, we know we're going right 1. Well, this is negative, so we know we're going to go down 1 and then right 1. So we go back, we go down 1, right 1, and we're on the line again. We go down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1. Okay? So this, again, was review a little bit, but it's also kind of pushing us into being able to interpret more data and words and charts and graphs, right? Because you guys mastered this whole, if I just gave you this, you guys know how to do this. Now it's trying to get you guys to be able to look at a graph and think a little bit and be like, okay, it said the initial height is 10, so that must mean it's the y-intercept. And the rate of change is 1 inch per hour. So we know it's getting lower, right? Obviously, the candle burning is not going to grow. It's going to shrink. So we know it's going to be -1 over 1. All right. Thanks for being on, guys. I appreciate it. We'll talk more about this tomorrow because I know it's tricky, especially once we get into data and all that and actually interpreting words and charts and graphs. But I really appreciate you guys being on. We'll talk more about this in class on Thursday. You got about 2 or 3 minutes here to head to your next class, which I believe is Mr. Puri for science. So head over to Mr. Puri's here in another minute or 2, and I will see you tomorrow. Well, I'll see some of you guys third bell, but you guys are dismissed. Thanks for being here.
Q marked me present.